Okay, so recall that in the last class we were motivated to essentially solve general classes of optimization problems. Right? We saw that a large number of engineering problems can be posed as mathematical optimization problems. So the end goal is to design or be able to understand how do you formulate a mathematical optimization problem and say something about the solutions, and also find out when you can find the solution to an optimization problem efficiently. And we want to develop this in the most general sense that is possible. We're not satisfied with just solving simple kinds of optimization problems, but also know where, if we develop a theory, we want to know what are the limits of this particular theory. What if, suppose we design an algorithm for solving an optimization problem, what is the broadest class of optimization problems that this approach can solve, and what classes of optimization problems can this not solve, right? So we want to understand both. So in order to do that, we'll need to develop some mathematical tools. So we'll go over some of the basics of real analysis and multivariate calculus in the beginning. So since this is essentially a course on optimization, we can't cover everything that we need to, but I'll still try to start from the basics and at least cover the essentials of what we need. Now, if you want to do things formally, then you have to essentially prove everything from scratch, which I will not be able to do. Right? After all, we want to get to the actual topic, which is convex optimization. But at the same time, we don't want to leave out any of the rigor in developing the entire subject. Right? So firstly, we'll just develop the mathematical formalism that is required. And in many places, I will not prove certain statements, but I'll certainly point you to references where you can find more details. Right. So I understand that there may be people from various backgrounds out here. Some of you may have already taken a course in real analysis and measure theory. Some of you may not have had any courses on real analysis. Some of you may have, at least I hope that most of you have done some basic multivariate calculus before. But in any case, we'll revisit all of that in this particular course. So we'll go pretty quickly. Because after all we are short on time, but you can, but I would advise you to go over the material again and go through the references that are provided on the website, and you'll need to you may need to revisit these topics as and when we go along this particular course, right? So let's start with sort of very basic stuff. Essentially, we'll start with subsets of R, but we'll go on to more complicated sets and so on. Right? So so the first, if you recall, I defined a mathematical optimization problem in standard form in a certain way, right? And one of the questions that was raised is, why did we define it in that particular way? And I didn't give a strong justification for it, but I essentially said that we want to ensure that when you're given an optimization problem, that optimization problem should have a solution. Whether or not you can find it is a different story. But the first question you should ask when someone gives you an optimization problem is, does this optimization problem have a solution or not? So we'll see a broad class of, so some of the analysis that we'll develop in the beginning is just to understand for what kinds of problems are we guaranteed to have a solution. What does it mean to have a solution, right? Okay, so first let's start with subsets of R. So we are given an arbitrary subset A of R, and we say that a number X is an upper bound for A if X is greater than or equal to Y for all Y in A. Right? It's the most natural thing. Again, some of this may seem too basic, but we just want to make sure that we're all on the same page as we go along. All right. So x is an upper bound for a set A if this x is greater than or equal to every single element of A. Most natural. And similarly, you're given a particular number for the same set A. We say that x is a lower bound for A if x is less than or equal to y for all y in A. Right? Okay. Again, basic case. So if I take the set which is the interval from 0 to 1, then any number which is greater than or equal to 1 is an upper bound for A, and any number which is less than or equal to 0 is a lower bound for A. Right? What is more interesting for us is the notion of the smallest possible upper bound, which we'll call the supremum. So we say that a number x, or let me call it x star, this is the supremum of A. Alright, it's denoted sup of A if it satisfies the following two properties. So first, x star is an upper bound for the set A. So x is greater than or equal to every element in A, but at the same time it is the smallest possible upper bound. So if you take any other upper bound for A, then this is smaller than that. So if x is any upper bound for A, then x star is less than or equal to x. All right. Let's suppose I give you the following set. A equals, again, the interval from 0 to 1. We know that any number greater than or equal to 1 is an upper bound for this set A. What is the least upper bound? What is the supremum? Yeah, it's 1, right? You're all convinced by this. Okay. Now, the supremum may or may not lie in this particular set A. For example, if I take A to be equal to the open interval from 0 to 1, once again, what is the supremum of A? 1. And why?
2, 3, 4 are all are upper bounds.
Okay.
Out of them, the minimum is 1. For example, if I take something like 0.99, but still again you can show some value like 0.999 which is more than this.
Okay. So how do you prove this formally? Okay. So let's suppose that what we want to show is that 1 is the supremum, right? So I claim that sup of A is equal to 1. So let's take any other number which is less than 1, which means that let's take 1 minus epsilon for some epsilon greater than 0. Any number which is less than 1 can be written as 1 minus epsilon for some epsilon greater than 0, right? Now if 1 minus epsilon is equal to supremum of A, right, can 1 minus epsilon ever be an upper bound for A? Why not? Exactly. So if you take 1 minus epsilon by 2, this is clearly greater than 1 minus epsilon, right? But that also lies in the set A. So clearly 1 minus epsilon is not even an upper bound for A, because 1 minus epsilon by 2 this belongs to A. So this cannot be an upper bound, because you can always find a number which is greater than 1 minus epsilon. Just take 1 minus epsilon by 2. This is an element of A. Likewise, okay. But on the other hand, if the supremum lies in the set A, then we say that it is the maximum. If x star supremum of A lies in A, then we call it the maximum. Note that the maximum may or may not exist for a given set, just by these two examples, right? So in this case, the supremum is equal to 1 and the maximum is also equal to 1. In the second example, A equal to the open interval 0 to 1, the supremum is equal to 1, but this set does not have a maximum. All right, that's a key point to keep in mind. Exactly as we define the supremum, we can define the infimum, which is the greatest lower bound. So we say that x star is the infimum of A, which I'll denote by inf of A, if it satisfies the following two properties. Can you tell me what those properties are? Yes, so x star is a lower bound for A, which simply means that x star is less than or equal to y for all y in A. And what is the second property that it has to satisfy? It should be the highest. So if x is any lower bound for A, then x star is definitely greater than or equal to x. Okay, and as we had in the case of the maximum, if the infimum lies within A, then we say that this x star is the minimum of A. And as before, the minimum may or may not exist for a given set. Now, some points to keep in mind. Now, it can so happen that the set A is not bounded from above. For example, suppose I take the following set 1 to infinity, or let us take the set of all real numbers, or let's say A is the set of all non-negative real numbers. Right? Is there an upper bound for A? Yes. Does this set have an upper bound? No, right? Because no matter which real number you can give, there always exists a larger near real number which lies within this particular set. So we say that the supremum of A is infinity. So infinity is not a real number, right? Infinity is just a symbol that we will use, which denotes that this is an, we say that that infinity is an upper bound, although it's not really a real number. Right. So if A is not bounded from above, then we say that the supremum of A is equal to infinity. And similarly, if A is not bounded from below, then the infimum of A is denoted minus infinity. All right. Another property which I will not prove is that every non-empty set has a unique supremum and an infimum. It doesn't matter which set you take. You can devise the most complicated subset of R. The set will always have a unique supremum and a unique infimum. Okay? So these are facts that we will use as it is. Okay? So every set has a supremum, every set has an infimum. It may or may not have a maximum and a minimum. Okay. So again, just to test our understanding, suppose that the set is the interval, the closed interval from 0 to 1. What is the supremum of A? This is 1. Infimum of A, 0. Maximum is 1, and the minimum is 0. Right. Similarly, in this case, what is the supremum? Yeah, it's 1. The infimum is 0. What is the maximum? There's no maximum. Is there a minimum? There is no minimum. Right. Now let's take the following set. It is the set of all rational numbers, which can be written as 1 by 3 to the power n, where n can take the values 1, 2, 3, and so on. Right. Now, where n is set of natural numbers. All right. For this, what is supremum of A? So supremum of A is 1 by 3. What is the infimum
0.
of A? This is equal to 0. Do you see why that is?
Because when it's tending to infinity, it is going to near to 0. But
okay, so at least you can see that if you take 1 by 3 to the power n, this is a decreasing sequence, right? And at least this is a simple enough sequence, and you know that it converges to 0. Right? If you take any number which is greater than 0, for any, say, epsilon which is greater than 0, you can find an integer n such that a positive integer n such that 1 by 3 to the power n is strictly less than epsilon. Right? So prove this. Right? So this means that no epsilon can ever be a lower bound for this particular set. Any positive epsilon cannot be a lower bound for this particular set. Okay, what is the maximum of A? Maximum of A. Now clearly the supremum of A is 1 by 3, and 1 by 3 belongs to this particular set. Therefore the maximum is also equal to 1 by 3. What about the minimum A? How many say that the minimum does not exist?
Precisely.
How many say that the minimum does exist and it's equal to 0? I thought you raised for both.
No, I didn't.
Okay, so why do you say that the minimum exists?
This exists in this set as a limit. So that the zero belongs to this set is my claim, and that is the minimum.
Okay,
Yeah, and
if
of the reason you mentioned for like for a set which is unbounded below minus infinity is the infimum. I just shift that.
it's the infimum,
Right.
it's the infimum, it's not the minimum.
Okay. Now, but because this is bounded, it becomes the minimum.
Okay, so let's get it clear. If a particular element has to belong to this set A, then you should be able to write that element as 1 by 3 to the power n for some positive integer n. Can you write 0 as 1 by 3 to the power n for a positive integer n? You can't, right? So therefore 0 does not belong to this set, right? So the minimum of A does not exist. It's similar to what happened in this particular case, right? So just because you have a sequence that lies within a particular set doesn't mean that what it converges to, if it's a convergent sequence, it doesn't mean that the limit has to lie within this particular set. And this is a classic example of a set where it's a discrete set, it's not a continuous set, and the minimum does not exist. So the infimum does exist, it's equal to 0, but the minimum does not exist. Right? Is that clear? Okay. Now, why does this matter? Supremum, infimum, maximum, minimum. In the end, we want to solve optimization problems, right? We want to know whether a solution to the optimization problem exists or not. And what does it mean to find the solution to an optimization problem? So suppose I have an optimization problem of the form maximum of some f of x subject to x satisfying certain constraints. All right. Now in this case, finding a solution means I should be able to find the maximum value of f of x subject to these constraints, and I should be able to find an x which satisfies the constraints and achieves that particular maximum or minimum, right? So now suppose that I have this problem that I want to maximize x square such that x lies within the range 0, open interval 0 to 1. Does this exist? No, right? On the other hand, the supremum of x square such that x lies within the open interval from 0 to 1, this does exist. What is this equal to? This is equal to 1. The reason why this does not exist is because, well, you know that the supremum of this particular function subject to the constraints is 1, right? But you can't find any x which satisfies the constraints and achieves this particular supremum. So really, if we want to design any algorithm, suppose the end goal was to find the solution. In this case, you can never achieve the solution. You can get close to the solution, but you can never achieve it. On the other hand, suppose the problem were to find the maximum of x square such that x lies within the closed interval from 0 to 1. Again, the maximum or the supremum in this case is equal to the supremum in this particular case. However, in this case, I can actually achieve it. There exists a point which is x equal to 1 that achieves the maximum. Right? It's precisely this class of problems that we'll design algorithms to solve. Right? So the solution or the optimizing x may lie inside the set, within the interior of the set, so to speak, or it could lie on the boundary. In this case, the maximizing x is x equal to 1, which lies on the boundary of this particular set. Right? But that's okay, because the boundary is well defined for this particular set. Right? Okay. So now let's look at more general functions and their properties.
You will only look at closed sets.
We'll only look at closed sets, yes. Which is exactly why, if you recall, in the previous class, we defined an optimization problem to be minimizing some f0 of x subject to the constraints that fi of x was less than or equal to some, say, 0, I equal to 1, 2, 3 up to m, and h I of x equal to 0 for I equal to 1, 2, 3 up to k. Right? These weren't strict inequalities. The constraints in the standard form that I considered in the previous class, the constraints were all of the form some function less than or equal to 0 or some function equal to 0. Right? With the hope that this defines a closed set. If I have strictly less than 0, then I have an open set, and so I may or may not be able to find a solution.
But this is still, the left it can go all the way down to minus.
It can go all the way down to
We are
minus.
okay with that.
That is okay for now. I mean, for now this was a standard form, so I want at least this to be satisfied. Right?
You want to find a supremum or infimum of a function,
Correct.
but which is not in standard form. Can you just add the equalities where it's not then solve for the minimum maximum and you can put the supremum?
Maybe, may not be. You have to be a little careful. Right? So typically, yeah. So just replacing the inequalities. Essentially, you take the set, and in some sense, you take the closure of that particular set. Essentially, you take the smallest closed set that satisfies your constraints, and then you can do your optimization over this new set, and that will give you the supremum or infimum that you wish to find. Okay, that will be jumping ahead. So again, let's recall some basic terminology and definitions related to functions. Right. So what is a function? A function is a mapping from one set to another. So I'll denote this mapping as f from this set A to this particular set B. So for every element in A, f assigns some element in B. The set A is called the domain, and the set B is called the codomain of the function f. Right? But not every element, so every element of A is mapped to some element of B, but it need not be the case that every element of B is a mapping of an element of A. So it may be possible that this f spans only a small subset of B. So the set of all elements that this f spans to is what we'll call the range. Right? So the range is always a subset of the codomain, but may or may not be equal to the codomain. And for any subset of the domain, let's say that I have some particular subset S. If you look at the set of all points that F maps to, so these points could be mapped to some other subset of the range. This set is called the image of F, image of S under F. Right, and that's what I'll denote F of S. So it is a set of all y in B such that there is at least one x in S with f of x equal to y. Okay, so right now we're just getting used to the mathematical formalism, just introducing some terminology and definitions. All right. So if you recall, f is said to be, the function is said to be 1 1 if no two elements of A get mapped to the same element in B. The function is onto if the range is equal to the codomain, and the function is bijective if f is both 1 1 and 1. Right? Nothing, just high school stuff. All right. So just to be clear, suppose I have the following functions from R to R. F of x is equal to 2x. Is this a 1 1 function?
Yes.
Yes, because every element x has exactly one element. So every element in the codomain has only one element that it's mapped to. Right? So it is 1 1. Is it onto?
Yes.
Yes, because using 2x you can generate any element in R. Right? So it's both 1 1 and onto. Let's take f of x equal to x square. Is this 1 1? It is not, because for example you take plus 1 and minus 1, both of these get mapped to the same element, which is 1. Right? So it is not 1 1. Is it onto? Yeah, is it onto? No, it is not, because you can't get a negative number as the so the image or the range is always the set of non-negative real numbers. You can't get a negative real number. So it's neither 1 1 nor onto. Let's look at f of x is equal to e to the power x. Is this a 1 to 1 function? It is a 1 to 1 function. Because e to the power x1 equal to e to the power x2 can only happen if x1 is equal to x2. Right? Is it a non-2 function? It is not, because e to the power x is always greater than or equal to 0. So the range is again the set of non-negative real numbers. In fact, the set of positive real numbers. Great. So that was some basics. Now again, we'll use this to define what is called a countable set. So we say that a given subset could be a subset of R, it could be a subset of Rn, it could be arbitrary. So this set is said to be countable if you can find a 1 to 1 map from the set of this set to the set of natural numbers. All right. How many of you have seen the notion of a countable set before? How many of you have not? How many have not seen what is a countable set? It's okay if you have not seen, but I would like to know. Right? Okay, then you should be able to answer the following. So is a finite set countable? Yes, it is a countable set, because you can find a 1 to 1 map from that to a set of natural numbers. Set of natural numbers, yep, just the identity map tells you that it is countable. Set of integers, yes, and can you find a map that How do you do it? So I want to find a one-to-one map from Z.
Start with 0 and then
Okay, so one solution is you can set let's say f of x could be equal to, let's say, 2x if x is negative and if x is positive, right? That's one way to.
With 0.
You'll have to shift it with 0. Okay. Plus 1 plus 1 1 if x is 0. All right. Okay, what about Z2? Set of all pairs of integers. Is this countable? It is countable because if you take any countable set and then a to the a, so if a is countable, then any direct product a to the k is also countable. Right? If you want to see a proof, here is a link. I'll let you go through it later. Similarly, set of rational numbers. How many say that the set of all rational numbers is countable? How many say that it is uncountable? It is not countable. It's okay, don't be shy. If you think it's not, it's not. Okay, so whoever said that it is countable, why do you say that it is countable? So,
Any set, any 0 to 1.
okay.
Between that, you can go on listing iterations.
So,
Similarly, for every
can you list all the irrationals?
all the listing all the data in that form. It's an exhaustive mapping.
Again, that's words, right? I want you to prove mathematically that it is countable. Yeah, exactly. So every rational number can essentially be written as in the form p by q, where p and q are integers, right? So effectively, there is a bijective mapping from Z2 to Q, right? Or Q to Z2. So every element which can be written as P in the form P by Q can be represented as a pair P comma Q, right? Is that point clear? You take any rational number, this rational number can be written in the form P by Q. Right? This representation is not unique because the number 1 by 3 can also be written as 2 by 6. But I can certainly represent this as a pair of integers. Every P by Q can be represented as a pair of integers P comma Q. And therefore, there exists a one-to-one mapping from Q to Z2. Right? So there exists a one-to-one map from Q to Z2, and we know that Z2 is countable, right? So there exists a one-to-one map from Z2 to the set of natural numbers.
Should be there, right?
Why?
Because of this non-uniqueness, so 1 by 2, 2 by 4, etc., that itself is an infinite set.
One, correct. No, but doesn't matter, right? So you take any integer, any rational number, right? You can represent it as, let's say, in the most simplest form you can. So let's say 1 by 3. Let's take 1 by 3. 1 by 3 can also be written as 2 by 6. But I'm going to map 1 by 3 to 1 comma 3.
Which will exclude pairs like 2 comma 6,
That's okay.
3 comma.
So all I'm saying is that there is a one-to-one map from Q to Z2. It is not onto, right? So there is no point that maps to 2 comma 6. That's okay, right? There is some point which maps to 1 comma 3, right? But definitely this map from Q to Z2 is one-to-one, right? For every element in Z2, so 1 by 3 is mapped to, 1 comma 3 is mapped to only by 1 by 3. No other rational number maps to 1 comma 3, right? That's something that you agree with. So this map is one-to-one, not onto, which is fine. But there's also a one-to-one map from Z2 to N, because Z2 is countable.
Your last.
Yeah, that's just the previous thing, right? So if you take the composition of these two maps, that's still going to remain one-to-one, right? And therefore, the set of all rational numbers is countable. Right? So think about it later on. Right? Okay. So if you have a set that is not countable, in the sense that it is impossible to find a one-to-one map from the set A to the set of natural numbers, then we say that the set is uncountable, right? For example, the set of all real numbers, the closed interval 0 to 1, is uncountable. If you want to see, there are a number of proofs for this particular statement. Here's a link to one particular pictorial proof. Similarly, the set of all real numbers, the set of all complex numbers, all of these are uncountable, right? In general, if you're thinking about optimization, designing optimization problems, we're always going to consider uncountable sets, right? As soon as the region over which you're optimizing becomes discrete, it becomes computationally very hard, which is rather surprising, right? You would have imagined that finding an efficient optimization algorithm would be easier if the space over which you're optimizing is finite or discrete, and more difficult if it is continuous. But as it turns out, for a large class of optimization problems, it's easier to find the solution if the space is continuous rather than discrete. And in fact, when you want to solve optimization problems over discrete spaces, typically the first approach that is used is relax the problem so that you do optimization over a continuous space. Okay, again, some more definitions. So over the space of real numbers, or over Euclidean spaces, we have this notion of a distance, right? And basically, what is a distance? A distance is the Euclidean distance is a specific instance of what is called a metric, which you can define over arbitrary sets, right? So what is a metric? A metric is any function which takes pairs of elements and assigns it a real number. So for every pair of elements, this metric always has to be greater than or equal to 0, and if those 2 points are distinct, if x is not equal to y, then the distance between them, or the metric, should be strictly greater than 0. Right? If you think of the notion of distance, you take any 2 points, the distance between those 2 points is some non-negative number, and the distance is 0 only if you're measuring the distance from one point to the same point itself. If you take any 2 different points, then the distance is strictly positive, right? And the distance from x to y is the same as the distance from y to x. So it's a symmetric function, and the distance also has to satisfy a triangle inequality. Essentially, you take any 3 points, right? The shortest, the distance from x to z is always going to be less than or equal to the distance from x to some point y plus the distance from y to another point z. Right? So it has to satisfy. So any function that satisfies these 4 properties is called a distance or a metric. The most common example is the Euclidean distance that you're all familiar with, right? But more generally, you can define other notions of distance in Euclidean space itself. So one example is what we call the LP distance. For some p greater than or equal to 1, I'll define the LP distance from x to y as this particular function. So it is summation I equal to 1 to k. I'm looking at LP distance in r to the k. So it's just sum over all the components mod xi minus yi whole to the power p whole raised to 1 by p. Right? It's possible to prove that this is a valid distance. It's a metric.
We change to Minkowski inequality means triangle inequality, and triangle inequality we need to apply inequality in P dimensions.
Not necessarily, right? All right. Similarly, we have what we call the L0 distance. So given any 2 vectors, the L0 distance, also called the Hamming distance, is simply the number of components in which the 2 vectors differ. All right. And similarly, the L infinity distance is the maximum of overall the components in which they differ. Right? But here is also an example of some function which is not a metric, which does not form a distance. If you take L2 norm squared, right? So L2 norm squared of x minus y, this is not a metric because it does not satisfy triangle inequality. All right. Just as we defined a distance, we can define the length of the vector of a given vector, uh, which we call the norm of a vector. So if you take any arbitrary vector space, a function is said to be a norm over this particular vector space if it satisfies a similar set of conditions, just as we had for the distance. So the norm of a vector is always greater than or equal to 0, and it's equal to 0 only if it's the 0 vector, right? And it satisfies this scaling property. So if you take a vector, scale it by an amount alpha, then the length increases by an amount alpha, right? So f of alpha times x, the norm of alpha times x is mod alpha times the norm of x. And it also satisfies a type of a triangle inequality, which is the norm of x plus y is always going to be less than or equal to the norm of x plus the norm of y, right? And you can see immediately by comparing the two definitions of metric and norm, if f is a norm over a vector space, then f of x comma y, x minus y forms a metric. So using a norm, you can always construct a metric. But in order to define a metric, it does not, the underlying space need not necessarily be a vector space. In this case, it has to be a vector space because we need the notion of a zero vector, and we also need this notion of scaling and addition. So linear combinations in general. Right? So just something to keep in mind, I'm going pretty fast, so you need not write down everything at this particular point, because right now I just want to go over the definitions and make sure that you're familiar with it. So once the class ends, please go back, revisit the definition, see some more examples, try to construct your own examples of what would be a norm, what functions would not satisfy a norm, what functions would be metrics, which functions would not be metrics, and so on, right? All right, so similarly, we also, for a given vector space, we have this notion of the dot product or the inner product between two vectors. So an inner product is just again a function which takes two vectors as input and outputs a real number, and it has to satisfy these three properties. That is, the dot product is symmetric, f of x comma y should be equal to f of y comma x. The inner product between a vector and itself should be greater than or equal to 0, and should be strictly greater than 0 if x is non-zero, right? And it also has this linearity property. So if I take the inner product between alpha x plus beta y and another vector z, then it's equal to alpha times the inner product between x and z plus beta times the inner product between y and z. All right. Again, this is something that your standard inner product satisfies. So let's just verify that the standard dot product that you've seen in high school is actually an inner product. Does it satisfy property 1? So if I take A to be Rn, the vector space to be just Rn, then, and I take this particular function, is this symmetric in x and y? Yep, because f of y comma x is summation over all I yi xi, which is the same as summation over all I xi yi. So it is symmetric. Is it non-negative. So if I take f of x comma x, then what do I get? It's just summation I equal to 1 to n xi square, and xi square is summation xi square is greater than or equal to 0, and it's equal to 0 only if all of the xi's are equal to 0. So it satisfies the second property. Does it satisfy the third property? Third property is f of alpha x plus beta y and z. What is this equal to? It's equal to summation over all I alpha xi plus beta yi times zi, right? Which is equal to, well, I can first write this as summation over all I alpha xi zi plus summation over all I beta yi zi, which is the same as alpha times summation over all I xi zi plus beta times summation over all I yi zi. Right? Okay. That's okay. It was just a sanity check to make sure that our standard, the dot product that we've seen, is actually a dot product. But now let's look at something a little more interesting. So let's say A is R2, and let's look at the following function f of x comma y is x1 y1 plus 2 times x2 y2. It's not x1 y1 plus x2 y2, it is x1 y1 plus 2 times x2 y2. Is this an inner product? Does this satisfy all of the three properties that I had over here? So firstly, is property 1 satisfied? Is f of x comma y equal to f of y comma x? It is, right? So property 1 is satisfied, not a problem. Let's look at the second property. So f of x comma x should be greater than or equal to 0, and it's equal to 0 only if x is 0. So what is f of x comma x? This is x1 square plus 2x2 square, which is greater than or equal to 0 for all x. And the only way this can be equal to 0 is if both x1 and x2 are equal to 0. So the second property is also satisfied. Great. Now let's look at the third property. F of alpha x plus beta y and z. This is alpha x1 plus beta y1 times z1 plus alpha plus 2 times alpha x2 plus beta y2 times z2, right? Is this equal to alpha times f of x comma z plus beta times f of y comma z? It is, right? Alpha so it also satisfies the third property. So this this weird thing that I have defined over here is also a valid inner product. It also corresponds to a dot product. All right.
Can you prove it like by saying we anyways know that for three-dimensional vectors, the usual inner product and we're taking a subset of the second component, third component, which will obviously work.
I'm sorry, I didn't follow.
Like, if we, in the first example, we take n equals 3.
Okay, sure.
Obviously works.
Okay.
Now we're taking a subset of those vectors.
What do you mean?
We're taking the vectors in which the second component is equal to the third component. So obviously this function is x2 equals x3.
Okay. So for that, let's look at the next example. All right. Let's look at f of x comma y, which is x1 y1 minus 2x2 y2. Right. You could, in principle, pose what you said in the same way, right? Wherein the third component is whatever, maybe minus 2 times the second component, right? So, but let's see if this is an inner product or not. All right. So the first property satisfied. Is it symmetric in x and y? It is symmetric. That's not a problem. What about the second property? It can be negative, right? For example, if I just take the vector x equal to say 0, 1, f of x comma x is minus 2, which is less than 0. So this is not a valid inner product. Right? So in this case, there was this positive linear combination of the xi yi's that nicely gave us a valid inner product, but this sort of this linear combination of the xi yi's does not give us a valid inner product. Is it possible to say when linear so in general I could cook up something even more different. For example, I could say x1 y1 plus 2 x1 y2 plus 3 x2 y1 plus 4 x2 y2. It's some function. Is this a valid inner product? In general, suppose I take an arbitrary matrix A, an n by n matrix A, an n by n matrix A, and the inner product is defined as x transpose A1. All right. It depends on A. I agree. So the question is is the definition of this function clear? So I have a matrix A, some n by n matrix A, and the inner product between, or whatever, this function f of xy is defined as x transpose A times y. So if I look at the second example, right, what is A in the second example? It's diagonal 1, 2, right? If I take A equal to 1, 2, then this basically reduces to this definition. Okay, so this is a special case of this particular function. Similarly, what is this? What would be the A matrix in the third example? It's diagonal 1 minus 2. All right. So both of these are special cases of this instance. Now let's look at it. What is the first property that needs to be satisfied? Symmetry, right? We want this to be symmetric. So what is f of yx? It is y transpose ax which is also equal to X transpose A transpose Y, because this is a number, the transpose of this is the same number, and the transpose of this is X transpose times A transpose times Y transpose transpose, which is Y. All right. So,
Equal to A.
yep. So, for A to be a valid inner product, A should be symmetric. If A is not symmetric, then this will not be a valid inner product. Right? A must be all right. So that's a requirement. I'll skip to property number 3. Is property number 3 always satisfied? What is f of alpha x plus beta y comma z? This is alpha x plus beta y transpose a z, which is nothing but alpha times x transpose a z plus beta times y transpose a z. So this is alpha f of xz plus beta f of yz. So the third property is always satisfied irrespective of what the matrix A is. Right? Now let's look at the second property. What do we want? We want to make sure that f of x comma x is always greater than or equal to 0, and it's equal to 0 only if x is 0. Right? So f of x comma x is x transpose ax, and we want this to be greater than or equal to 0 for all x. In fact, we want this to be strictly greater than 0 for all x not equal to 0. What property should A satisfy? It should be positive definite. Right? We'll revisit positive semi-definite and positive definite matrices later on, but this basically says that A must be positive definite. All right, so as long as you have a matrix A which is symmetric and positive definite, you can define an inner product. Right? So another way of thinking about this is that you can try to think of, so you know that A is symmetric, right? And as we'll see later, symmetric matrices can always be diagonalized. So if you take the diagonal representation of A, right, suppose that you can write A as some P transpose dP, where D is a diagonal matrix and PP transpose, as we'll see, can be chosen to be orthogonal matrices. So X transpose AX is just X transpose P transpose D Px, which is Px D Px. So the geometric interpretation of this is you take X you transform it. You essentially change the basis to something else and then measure the inner product with respect to this basis, except that the inner product is just a scaled version or a linear combination of the xi, yi's. And this is guaranteed to be an inner product as long as all the diagonal entries are greater than 0. Right? D should be greater than 0. All the diagonal entries should be greater than 0. All right. Any questions so far? Okay. Again, I'm jumping topics from one to another, but so you really need to go back to all of these topics once the class is over. So let's look at sequences. What is a sequence? A sequence is just a list of an infinite list of elements from a particular set in some particular order. Right? Or mathematically, it is just a mapping from the set of all natural numbers to this particular set. So A1 is some element of A, A2 is some element of A, and so on. And our interest is in defining sequences which sort of converge. Or in other words, what do you mean by converge? Eventually, the elements of the sequence are close to each other in some particular metric. So we won't define convergent sequences or convergence directly. We'll go through another extra step, which is the following. So we say that a particular sequence is a Cauchy sequence if the following happens. Essentially, if you look at the horizon of this particular sequence, you take any two pairs, any pair of elements in this particular sequence, they'll get arbitrarily close to each other. Right? So formally, it's Cauchy if for every epsilon greater than 0, there exists some positive integer n such that you take any two elements beyond n they're at a distance of less than or equal to epsilon. For example, let's take the following sequence 1 by 2 to the power n. Right? You take any arbitrary epsilon, let's say 0.1. Right? And you take an n large enough. You take an n1 and n2 that are sufficiently large. 1 by 2 to the power n1 minus 1 by 2 to the power n2, this will be arbitrary. This can be made arbitrarily small. Right? That's all that this is saying. So the main point is that you can define a Cauchy sequence irrespective of whether you know what the limit is or not, or whether the limit exists or not. Not every sequence is Cauchy. So for example, if I take the sequence 2 to the power n, Is this sequence Cauchy? No, right? It diverges. You take an n large enough. If you look at 2 to the power n1 minus 2 to the power n2, if n1 and n2 are really large, then mod of 2 to the power n1 minus 2 to the power n2 is going to be very large. Right? So this is not a Cauchy sequence, whereas this is a Cauchy sequence. Right? And a Cauchy sequence, assuming that your set A is nice enough, this will also be a convergent sequence. So no, n1 and n2 can be really large. They don't have to be adjacent to each other, but they have to be sufficiently large. If they're equal, then it's 0 for sure, right? So that's not interesting, right? But that's a good point that n1 and n2 don't have to be next to each other. I don't say that n1 minus n2 should be equal to 1 or anything. But both n1 and n2 should be sufficiently large. I can't take a small n1 and a big n2. Right? Is that okay? All right.
Equality should come, or you can ignore the equality.
Which one?
Equality is less than epsilon is sufficient equality, or less than equal.
It doesn't matter at all. But for every epsilon, because for every epsilon greater than 0, I can make this less than or equal to epsilon. It doesn't really matter whether this is less than or equal to epsilon or strictly less than epsilon.
So if it works for one particular D, is it necessary for one particular metric D?
Yes.
Actually, that it should work for every other metric.
Not necessarily.
For example,
Well, metrics can get really weird, right? Because I can define a metric that is very different, for example, than the Euclidean metric. Okay, let's take the L2 metric versus the L0 metric. All right. So what does the L0 metric say? L0 metric says that you take any two numbers, the distance between them is 1 if they are not equal, and it's equal to 0 if they are equal. Now you take any convergent sequence in the, let's say 1 by 2 to the power n. If I take the L0 metric, this is not a convergent sequence, right?
This one is bounded, right?
It is bounded, yes.
Boundedness is not an issue for this question.
I didn't get your question.
Okay, right. Boundedness was weaker than convergence.
Boundedness is okay, sure. You can have bounded sequences which don't converge.
Okay.
Yeah. So I didn't get what you wanted to ask.
But he was asking if it is convergent for a particular metric,
Yes.
will it be convergent for other metrics?
The answer is
Your
no.
answer is no.
No.
So my question was, will it at least be bounded for all other metrics?
Will it be bounded for all other metrics? Okay. So you mean to say if it is bounded within one metric, is it also bounded with respect to another metric?
Yeah.
Again, I suspect the answer is no, because you can again come up with a very weird metric where it is not bounded with respect to one. All right.
what is the scale right to infinite of vectors or really bounded?
Which one? You can define all of this for infinite dimensional vectors also. Yes. Which? Yep. So we'll stop over here. If you want, you can leave. But if there are any questions, I can take them now. What was your question?
Orange color may not be good for the backside people. They may not be able to see orange color.
Okay, fine. I'll use a different.
Generally, blue, black, red will be the most preferable.